An action potential is a rapid rise in the voltage or potential difference across a cell membrane, followed by return to the original level. In normal circumstances, an action potential has the same amplitude each time it is evoked. There are no intermediate levels. This is known as an all or none response to stimulation. When applied to a cell membrane, the rise in voltage is termed depolarisation, while the fall is known as repolarisation. Depolarisation is defined as an increase of positive charge at the inner surface of the cell membrane. Repolarisation is the recovery of the membrane voltage or membrane potential back to its original value. This animation starts with the inner surface of a membrane having more negative charge than the outer surface. This is the normal situation in most cells of the body. The charge difference across the membrane can be recorded by placing an electrode on either side of the membrane and measuring the voltage difference across it. This is exactly how an action potential occurring at a cell membrane is recorded. During depolarisation, the inner surface of the membrane becomes more positively charged, reducing the difference across the membrane to zero. As charging continues, the voltage difference overshoots zero so that the inside of the membrane becomes more positive than the outside. During repolarisation, the charge difference across the membrane returns to the starting level. This is essentially what happens in the membrane of a real cell during an action potential. So, what causes the membrane voltage to change? It results from the movement of charged ions across the cell membrane. Ions are not uniformly distributed across cell membranes. For example, the sodium ion concentration is at least tenfold higher outside the cell compared with inside. That creates a large driving force trying to move sodium ions from the outside to the inside of the cell to even out the concentration. The opposite is true of potassium ions, which are around 30 times more concentrated inside the cell compared with the extracellular space. Consequently, there is a large driving force to move potassium ions out of the cell. However, the movement of these ions is prevented by the lipid membrane, which provides an impermeable barrier. There are proteins in the membrane that span the width of the membrane and can form a pore through the centre, allowing ions to move freely across the membrane. The pore can open and close to control the movement of ions through it. These proteins are called ion channels, and there are many different ion channel proteins, each one controlling the movement of a specific ion or mix of ions. For example, the red colour in this cartoon represents a sodium selective channel, or simply a sodium channel, which only allows sodium ions to pass through. There are distinct potassium selective channels, represented here in blue, that only let potassium ions through. Largely because of the concentration gradients across the cell membrane, when sodium channels open, sodium ions flow into the cell, and when potassium channels open, potassium ions flow out of the cell. But when these channels are closed, the ions cannot pass through them. This animation illustrates what happens during a typical neuronal action potential. It shows a membrane separating the outside of a cell from the inside. The pink layer represents the high extracellular sodium ion concentration, and the blue layer the high intracellular potassium ion concentration. Two main ion channels are involved: a sodium channel and a potassium channel. An action potential starts when the sodium channels open and sodium ions flow into the cell, causing depolarisation. Sodium channels open rapidly within a millisecond, then rapidly become inactive, so that sodium influx is a short-lived event. Potassium channels take longer to open, but when they do, they allow potassium ions to flow out of the cell to counteract the sodium influx and bring about repolarisation. What triggers sodium channels to open and start an action potential? They open in response to a small depolarisation of the membrane. But why? When the cell is at rest, it has a negative membrane potential, around -80 to -90 millivolts in neurons. In other words, the inner surface of the membrane is more negatively charged than the outside. Ion channel proteins span across the membrane, so they sit in the middle of an electric field. A region of the channel protein that traverses the membrane contains a repeating series of positively charged amino acids, which act as a voltage sensor, allowing the channel to sense and respond to the electric field across it. In a resting cell, the negative inner surface of the membrane attracts these positive charges, pulling them towards the inside of the cell and stabilizing them in a position that keeps the channel closed. As the membrane depolarizes, the attraction weakens, allowing the positively charged region to move up towards the outer surface of the cell and freeing the channel to open. The voltage at which it moves far enough for the channel to open is known as the threshold voltage. In neurons, that is around -55 millivolts. Membrane depolarization also leads to a shape change at the cytoplasmic end of the protein, which blocks the path through the pore and stops ion flow. This process is called inactivation. Because it occurs more slowly than the initial opening of the channel, sodium ions are allowed to flow when the channel opens, but only briefly, for about 1 millisecond. This helps to keep action potentials short. There are 3 distinct phases to the neuronal action potential. The upstroke depolarization mediated by sodium channels, as just explained, the repolarization, and the overshoot. The later phases both reflect the behavior of potassium channels. Just like sodium channels, potassium channels are also activated by membrane depolarization. So, when a membrane depolarizes and triggers the opening of sodium channels, it also activates potassium channels. But potassium channels are slower to open and they need a larger depolarization than sodium channels. That results in sodium channels opening first to create the upstroke, before potassium efflux becomes sufficient to reverse the effect of sodium ion entry and cause the membrane to repolarize. As it takes time for potassium channels to close, a proportion remain open when the membrane reaches its resting level. Consequently, potassium ion efflux persists and briefly drives the membrane potential to a more negative or hyperpolarized level until all the potassium channels have closed. That is the cause of the overshoot in the neuronal action potential. Neurons have a resting membrane potential of around -70 to -80 millivolts, at which most voltage-gated ion channels are closed. There may be small depolarizations of the membrane that dissipate and do not trigger an action potential. But if the depolarization is large enough to reach a threshold level at around minus 50 to minus 55 millivolts, sodium channels rapidly activate and begin the all or none action potential. Sodium ions flow through the channels, across the membrane and into the cell, causing further depolarisation and the upstroke of the action potential. A peak is reached when sodium channels inactivate and sodium influx is balanced by potassium efflux from the cell. As the action potential progresses, potassium efflux through the slower opening potassium channels dominates and causes the membrane to repolarise back to its resting level. The membrane potential returns to rest before potassium channels have had time to close, so potassium efflux continues, causing the membrane potential to overshoot the resting level and become hyperpolarised. The overshoot is short-lived as the closure of potassium channels causes the membrane potential to return to its resting level.